Well, a warm welcome to everyone to our webinar about simulating the transportation of dangerous goods, specifically EV batteries. Thank you very much for joining us today. My name is Paul Lethbridge and I'm the Director of Product Solutions Marketing here at SimScale, and I will be your host. Today's presenter is Dr. Ali Taleb. He's an application engineer here at SimScale. He has a background in engineering in EV power electronics and has a PhD in numerical simulation from Imperial College London. So let's take a look at today's webinar. So over the next 30-35 minutes, we'll start with a brief introduction to SimScale and why vibration analysis is important. Then we'll get into the meat and potatoes, the live demo, and we'll wrap up. We have enough time in about a 5-minute Q&A session, and also explain about your next steps for you to actually get started and try SimScale for yourselves. Please use the chat panel. It's there's a menu, pop-up menu, and there's a chat option. So please use that to say hi and feel free to ask questions. There's a question option under the chat panel. There's a drop down. And just a reminder that your microphones will remain on mute during the presentation. So first, a quick introduction to SimScale. If you're unfamiliar with us, we make high-fidelity engineering simulation, and importantly, we make it technically and economically accessible. It's all cloud-based. You access it through the browser, so it's very scalable. You can access it anywhere, at any scale in the cloud. I would say the three takeaway messages here are really, we make it very accessible. It's very easy to get access and to use. And we basically enable engineers to simulate and access and use engineering simulation without any compromises. And we also deliver best-in-class solvers and a pretty good user experience UI on demand. So why is vibration analysis important? Why are we here today? Well, basically, simulation can be used to understand a number of things. From a battery design perspective, you can use it to help with your design process to meet international vibration test standards, in particular the ones that relate to today's webinar, those that relate to the transportation of dangerous goods, but really any international standard or any testing standard you're trying to meet, simulation can give you a lot of insight into that. Particularly for EV batteries, before lithium cell batteries can be transported, they must have passed certain physical tests. You can't escape physical tests, but these tests simulate the transportation conditions like pressure, temperature, vibration, crush, and impact. So in this live demo, what we're going to do is we're going to virtually replicate a vibration test performed on physical test benches to evaluate the battery performance relating to the United Nations UN 38.3 standard, which is a long distance transport standard. Okay, so now we're going to get into a live demo.
Thank you very much, Paul. Hello, everybody. So today we'll be performing a virtual shaker table test where we replicate the UN 38.3 standard using a templated simulation workflow. We'll be considering two different designs or two different models. One is an electric vehicle battery module, and the other is a standalone housing concept. And you see the two cases here on the left. And the simulation will take two steps. So the first step is a modal analysis to find which frequencies or which eigenmodes can be dangerous during the UN 38.3 test. And the second is a harmonic analysis to see the vibration response that happens during the physical test. The objective of this simulation is to quantify the risk of resonance, but also to quantify vibration magnitudes, peak stresses, and to see if we comply with the UN 38.3 standard. So this standard is valid since January 2020, and it demands for any shipment of lithium batteries to provide proof that they've passed the 38.3 T3 vibration test. So what does this test entail? So during the test, cells and batteries are firmly secured to the platform of a vibration machine. And the vibration is a sinusoidal waveform with a sweep between 7 Hz and 200 Hz. From 7 Hz, a peak acceleration of 1 g is maintained until 18 Hz is reached. Between 18 Hz and 50 Hz, the acceleration is increased to 8 g, and this is then maintained as the frequency is continuously increased up to 200 Hz. And to pass the test, no leakage or venting or rupture or fire can occur. So how does FEA help within the context of such a test? Well, structural damage or structural failure is the main cause of leakage and venting or ruptures within batteries. And these in turn lead or increase the risk of fires. So a design engineer has to ensure that stresses during vibration do not exceed minimum factors of safety, and must ensure that deformation does not lead to any clearance issues. Right, so let's jump into the platform where I can show you how we can carry out such a simulation. Okay, so you should see now my browser window. Yeah, so this is my Chrome browser. And what you see in the browser is SimScale. So SimScale is a cloud-native, web-based simulation platform. So everything you do in SimScale is in the cloud. This means you don't need to install any local software on your local machines or in your network. Which this in turn means you don't need any sophisticated hardware. You don't need any sophisticated software maintenance. All you need is a laptop or a computer and a stable internet connection. Yeah, all the heavy lifting of the simulation calculations are carried out in the cloud and by very powerful machines. And so what we see here, I'll reload the website so we can see the geometries. So we see here the battery module that we're going to consider first before we move on to the housing. Yeah, and for this battery module, we carried out a modal test, a modal analysis, and also a harmonic analysis. We'll jump first into the modal analysis so that we can understand what eigenfrequencies we're dealing with. Yeah, and we can see here very quickly in the simulation table. We'll go into that a bit more in detail later on. Mainly what the boundary conditions are, and we have a fixed support here on the bottom, and also here in these drill holes. So these are the points where the battery model is connected to structure, and so these points here, or these faces here, are fully constrained. And so after carrying out a simulation where we survey for the first 10 modes, you can see here what the eigenfrequencies are. And we see here that the very first eigenfrequency is at 233 Hertz. So that is already above the 200 Hertz limit of my UN 38.3 test. So that's already a good sign. Right. If we have a look at the shaker table test, so here we're dealing with the same boundary conditions, obviously. So the same fixed supports. And further boundary condition is the base excitation. So base excitation basically tells me that in this case, in Z direction, I have defined the following accelerations. So between 7 and 18 Hertz, I have 1 g. Between 18 and 50 Hertz, I'm increasing from 1 g to 8 g linearly. And then from 50 to 200 Hertz, I again have the 8 g maintained constantly. And in this case, it is applied in the Z direction, yeah, sinusoidally. But we also carried out the same simulation for the X and Y direction, right? Because that needs to be tested in the UN 38.3 standard. Well, we can have a look at some of the results. Mainly, we're interested in displacement and in stresses. Okay, so let's firstly have a look at the displacement. Okay, so we're here at 200 Hertz, yeah, the very maximum of our test. And we're visualizing here displacement. We can also animate the mode so that we see how the model is vibrating. But we see here, up here, it seems to be the highest displacement in green, so that's around maybe 1 millimeter. And the maximum displacement within the whole assembly is 1.8 millimeters, which would be it's hidden here, but it's inside, some part inside it is displacing by 1.8 millimeters. So that's a maximum displacement, which is a very moderate displacement. And we can assume that there will be no clearance issues due to this displacement. The next step would be to look at stresses. So let's visualize the stresses. I'll stop the animation. And we see here in the outer casing, we have localized stress regions or peak stresses, especially around the area where it's connected to structure. And this casing is an aluminum alloy with a yield strength of about 100 megapascal. We have a safety factor of 2, so we do not want generally the stresses to exceed 50 megapascal. However, as we zoom in here, we see that we have regions that are around 100 and even at these corners go well beyond 100 megapascal. You can visualize this even a bit more by looking at this ISO range. So now I will create ISO volumes where the stresses exceed 50, so they are between 50 and 180 megapascal. And if I increase the transparency or the opacity of the whole assembly, and we can see here I've got my localized peak stresses here and also on the other side. Yeah. And even around these very sharp corners, we have extremely high stresses, which may be due to singularities. So this area might need a mesh refinement to see if actually these stresses really go this high. Or another design consideration that can be done is maybe to round this corner off with a fillet or a radius to avoid stress concentrations like here. But if we look at anywhere beyond this constrained area, we see that actually the stresses are all below 50 megapascal, and so we're in a safe region. Okay, so that concludes the battery module. It seems to be a safe design. It seems very likely to pass the UN 38.3 test. Let's have a look at the housing over here, right? And I'll show you how to set up a simulation, the shaker table test, with this template down here. And then in the next step, we can look at the results, right? So obviously the first step to do here is to carry out a modal analysis. I won't cover how to set up a modal analysis here. It's fairly straightforward. Okay, here we have a ready-made template where we just need to fill up the simulation tree such that these red rings turn into green check marks, and then we can run the simulation. And what has already been prepared within this template is the base excitation, right? So here again, we have the directions. Let's say we want to first start with the Z direction, or we can start with the X direction. Actually, that's fine. And we have here the table for the applied accelerations. And also here in simulation control, the frequency list is also prepared for us, starting from 7 to 200, the frequency stepping of 10. Yeah. Right. So we'll work down this simulation tree here. First thing is the materials. So there are two materials in this assembly. One is neoprene, and the other is aluminium. So we don't have neoprene here in our default materials, so I can choose actually anything here, and then I'll change the material properties here manually. So I'll rename this as neoprene. The properties of neoprene are 1 times 10 to the power of 8 Pascal for the Young's modulus, slightly higher. Slightly higher density. And now the assigned volumes are all the gap fillers here. Perfect. Now the next material is aluminium, and all the rest of all other parts in this assembly are made of aluminium. So I'll choose a gap filler, invert that, and thankfully aluminium is obviously one of the default materials. Apply that, and that's done. Now the fixed support, that's an important boundary condition because that actually highly influences your vibration response and also your eigenmodes, obviously. And so it's fixed here through these drill holes where where it's screwed to the structure. Quite a few of them to choose from. That's our last one. There we go. I'll define this as a topology set so that I don't need to, if I need to do it again, I can just do it with one click like that. Right. So in the future, so actually I can just delete it now and just do it again, and then we'll see how quickly that goes. Fix support there. Done. There you go. Right, and normally if you have a template, that's how easy it is. All we need to do now is start the simulation. Yeah, so I did this in X direction, so I'll call this simulation X direction. I'll start that. And now I also need to do the Y and Z directions, right? Because the test has to be carried out for 3 perpendicular directions. So we'll do the Y direction as well. And lastly, the Z direction. There we go. So now we have 3 simulations that run perfectly parallel to each other. So for each simulation, a new virtual machine is set up in the cloud. So that means if one simulation takes 2 hours, all 3 simulations will also be finished after 2 hours. Okay, so this won't finish within the time of this webinar. However, the results already have been prepared, just like in a cook show or a cooking show. And we can have a look at the results here. So here is the shaker test for the housing has already been finished. You can see here it's all green, and the modal analysis has also been carried out. So let's start with the eigenfrequencies and have a look what the first 10 modes are. And we can see here for the housing, we've got eigenmode 1, 2, and 3 all below 200 hertz. So that's already a red flag. In the physical test, we will be going past 3 different resonance cases, which can lead to very high amplitudes of the vibration response. So that can be quite problematic. And we can now go into the results of the shaker test itself, and we'll look at the Z direction because that is the most problematic one. Okay, so let's start with the displacement. Okay, so we're looking here at 147 hertz, which is close to the third eigenmode. Yeah, and we see here we're dealing here with a maximum displacement of 4 millimeters. Yeah, I'll increase here the or reduce the opacity a little so we can see a bit more what's happening on the inside, like this. Or we can keep actually maximum and hide this face right here. There we go. So we see here this middle plate here actually oscillates quite strongly. We can animate this if we wanted to see in which direction it's moving or how it's moving. Oh, let's go back to 147. Here we go. You can see which way it's moving back and forth. Yeah. Next up, let's have a look at the stresses. So, carry the stress here. And we'll find maybe here stress of 180, for example. Yeah. So are we seeing here we have pretty high stresses in extended regions. Actually, it seemed to go beyond even the 180 megapascal. Or if we keep this at 100, let's say, see that, okay, actually we exceed the yield stress in many regions. Or if you look at the isovolumes again, for anything from 50 megapascal upwards, and let's make this, let's say 300, and we make the whole part the opaque, and we can see here that actually we're exceeding 50 megapascal in many areas, and we're actually exceeding the yield stress here. Everywhere it's red, we're exceeding the yield stress of aluminium. So this is a giant red flag, and there is a high probability that the part may fail during the test, especially as it reaches this this frequency around 147 hertz. Okay, so let's go back to our slides. So this is a summary of our results. So on the left here, you see the results for the EV module. We had maximum displacement in Z direction of 1.8 millimeters. Yeah, and peak stresses mainly in this top part here, where we reached areas above 50 megapascal. However, as we move away from there, everything is below 50 megapascal. Whereas for the housing, we had very high displacements of 4.3 millimeters, which could lead to issues, and also very high stress regions here and here. But also here were the stress regions that were above 100 megapascal, but we have very extended areas that have stresses above 50 megapascal. Okay, so let's put on our hats as design engineers here, or let's put ourselves in the position of a design engineer. If we're looking at the EV module, yeah, there were no resonant frequencies within the test frequency range. The displacements were quite low, all the way up to 200 hertz. The 200 hertz, which is the very limit, where the one was the most critical frequency. There were some errors with some high stress regions. Maybe local peak stresses were due to singularities at the corner. Yeah, so maybe further analysis might be required in these areas, in these corners, to actually really understand, is it due to sort of issues with the mesh, or is it actually, or do we actually have to deal here with the high stresses, and what can we do to mitigate that? Maybe round these corners off, for example. But as we move away from those areas, we are actually satisfying the minimum factor of safety of 2. So all in all, there's a low risk of structural damage, and so there's also low risk of that we'd fail the UN 38.3 test. So as a design engineer, I would say we can move on to actually carrying out the physical test for this design. Now, if we look at the housing concept or the housing design, we have 3 resonance frequencies within the test range. So resonance will be an issue during the physical test. The displacements are quite high, around the 140 hertz, which is close to actually one of the resonance frequencies. So that could lead to, or will lead to, clearance issues. And also we have very high stresses throughout large parts of the design. Yeah, many of them well beyond this yield stress, and we are definitely not satisfying the minimum factor of safety requirement of 2. So all in all, there is a high risk of structural damage occurring during the physical test, and therefore the test will likely fail. And so further analysis, not just further analysis, but also design changes are required before we move on to carrying out the actual test. So the aim should be of the design revision is to maximize the lowest eigenfrequencies, to move the eigenfrequencies beyond the 200 hertz limit, and that way we'd avoid resonance altogether. Right, so that concludes the live demo, and I'll hand over back to Paul to move on to the Q&A. Thanks very much, and thank you for your attention.
Thank you very much, Ali. We had a few questions come in during the chat, and Ali, if that's okay, we're a little bit over time here, but maybe I'll just pick out a couple of questions and let's do it.
Sure.
So let me see. So one person asked, so this is all done in the browser. Obviously, you saw a number of browser windows open, simulations running. So what browsers are supported?
So you can use SimScale with any browser, pretty much. The one that is supported the most is Chrome. However, it works with Firefox, with Safari, with no issues. But we generally recommend to use Chrome because that's what we test with.
Ali, thanks very much. Another question: how long does a simulation like this take to run, and what is the core hour consumption?
Yeah, so how long a simulation takes strongly depends on the complexity of your simulation. So, for example, the housing concept, the modal survey just took 10 minutes, and then the vibration analysis took 40 minutes. We were using 4 cores. So let me have a quick look as to, I have it right here. So yeah, so the housing took 95 minutes, so an hour and a half to run the full vibration test. And using 4 cores, that was 6 core hours. Now, if you want to make it run more quickly, you can use 8 cores up to 64 cores, and that can greatly increase your speed. But then obviously your core hour consumption will also increase.
Mm-hmm. Ali, thanks very much for explaining that. Brilliant. Okay, well, we had a few other questions come in, but we are out of time. I've got one more slide to wrap up here. So what we'll do is we'll get back to those attendees that are attended here with an email with other questions that you've asked. And so with that, let's just get on to our last slide here, which is really all about our next steps. So I hope, after seeing Ali's excellent demo there and taking a look at the vibration analysis, sort of things you can do with SimScale, you're now raring to go to try it for yourself. So you can request a demo by basically visiting simscale.com, or you can contact us, of course, directly at sales@simscale.com. And basically, when you do that, an application engineer will be in touch with you within 1 business day, within 24 hours, to basically learn a little bit more about what you need and get you set up with a hands-on session. So the other thing to say is that we will send a link to a recording of this session, so that if you want to run through it again, you can, or if you've got some colleagues who weren't able to make it today, you can share the link with them and they can also take a look at it. So with that, that brings us to the end of our webinar. I want to thank you all very much for attending. Thank you.